great pleasure to introduce Dr. Debraj Rakshit, who's going to
Huh.
talk to us about Twistronics via cold atoms. Debraj is a good friend of mine and my colleague at HRI. And Debraj got his PhD from the Washington State University, working with Dorothy Bloom, and then followed it up with postdocs at HRI and Poland and ICFO. And he's now back at HRI doing some very exciting stuff. So looking forward to listening to Debraj. Debraj, go ahead.
Thank you, Sam. I didn't know that you are going to introduce me. That's a nice surprise. Uh, okay, so let's begin. So I'll talk about something called Twistronics, and I'll tell what it is. And obviously, there's cold atoms. So we are going to talk about ultra-cold atoms and quantum simulators, basically the idea of quantum simulators. But we'll focus on Twistronics. So invariably, my background is mostly in quantum information theory and ultracold gas also. But then I will talk about a lot of stuff from condensed matter physics, although I am not an expert because this is a work in interface. We'll see how it goes. So let's say that what is it's all about, where it all began from. So I'll just start showing. You see that on the top there is a fun picture, like there is some fancy cloth, and there are some patterns that you can see. I don't know if you can see or, but yeah. So these patterns, there is a French term. It's called Moire pattern, and this kind of pattern generations that happens in solids. So when you create, let's say some 2D material, and then you put another 2D material on top of each other and try to play with their orientations, relative orientation by changing their rotations. Then you can see different kind of interesting patterns are emerging. So you can actually, what you are doing, that you are rotating. It could be any structure. It could be a graphene structure. It could be some 2D square lattice. Doesn't matter. Okay, but as you will change one's relative position with respect to another through a rotation, then you will create, say, larger unit cells. Okay, so I have a video that I can show. So here you are seeing that as I am doing this rotation, so one layer is rotating with respect to other layer. You are seeing this different kind of crystalline structures are emerging. So basically, what it gives solid state physicist or the condensed matter physicist a very one thing that they didn't have, the control over creating lattice structures, because always we are bound to by what nature is providing us. So we do experiment on that. But now you see that by this kind of manipulation, you can create different lattice structures, and you can create something that will give you very interesting physics that will follow it. So this is like, so it will follow from the band structure. If you go to the single particle picture first, and so graphene band structure is very well known. So this is a single here, this is, so I think there is a way, sorry. Yeah, so this, yeah, so I'm trying to create a laser pointer. So this is a single graphene structure, there are diacoms and things like that. But then you put one graphene and single layer and put another graphene single layer on top of each other, and then try to do slow rotation of with respect to each other, and you will see that invariably what you will create different unit cells which actually has thousands of lattice sites in a single unit cell. And then you may get some periodic or quasi-periodic patterns that will emerge. And for example, in this plot, like okay, so I'm not getting this, but at the bottom plot, this one where I am showing so there is like a different 2 degree, 1 degree, 0.7 degree. Okay, so these are like when your relative angles between two layers. and you see how the band structures are emerging. So what interesting happens that when you are very close to like something like 1.1 degree, you see that the middle band, which was very dispersive in its nature, it becomes flat. And then there are two Diracs that are almost touching it. There's a small gap between them. And then you increase this rotation again, and then band becomes dispersive again. So where this band is, flattening, uh, okay. So where the band is flattening, then there is some interesting physics, very interesting physics will emerge. Okay. So what happens that when band starts to being flattened? So you think that, okay, so we have a very busy life and we are always running and we don't have time to talk with each other. Okay, so that's like that's like this dispersive band. So the electrons are very fast. They are not interacting in such a way that could make them talk with each other. So when you start flattening the bands, what happens that this electrons slows down, and then you almost stop them. Okay, so because the dispersion, it doesn't depend. Okay, so these slow electrons then they have more time to interact with each other. They start talking, and then you start to get very beautiful things. Okay, so you can think it like that. It's totally correlation dependent physics that you are getting there. Okay. I have a video, so most probably I will show that for fun, that how with angle, how the band structures is emerging. Okay, so this is like this. So you see, oh, you start noticing the angle also. Okay, and the angle is decreasing. Now see what happens when you are very close to 1 degree. So now it's going towards this 1 degree. Okay, so now you see that it started the middle band, the dispersive band starts being flattened. And now it's completely flat, 1.1 degree. Okay. So this is called a magic angle. And then you can keep on playing this game. And then at even smaller angle, you will keep on repeating the similar kind of band structure. So so there are a set of angles where this kind of band structures will repeat, like the flat band and the Dirac cones and things like that. And so these particular angles are called magic angles. So what happens actually? So this first, let's talk about the paper that came from the MIT group. Harare led it, and so there is this. So this is like the 2018 Nature paper. So the first paper was like that. So this saw that at unit filling that there is this so as you change your carrier density and look into temperature, so on y-axis there is temperature, so there is this superconducting dome, and then there is some insulating phase that's happening. So now that was the very first experiment. Okay, so this may remind you also very close structures like Fermi-Hubbard model. Okay, so there also you'll know that okay, there are certain things like that. Okay, so it will remind you something like that. So now a more clean experiment was done from a group from IQFO. Okay, so that's led by Efitov, Dmitry Efitov, and so they also had a set of papers. But the first paper that they did, where you can see these things very clearly, and you will see that okay, so there is this repeating superconducting and correlated insulating phases. Okay, superconducting. So the superconducting dome is there, and then you change the density, you get a correlated insulating phase, and it all happens at whenever there is an integer filling. This happens. Okay, so it's not only for a particular filling, but it happens for all integer fillings. And then it was followed by a lot of other interesting experiments. and people try to understand what's happening. So this superconducting phase that they get, that's actually not conventional superconducting phase that we usually talk about, but there are different means aspects of unconventional superconductivity is going on, things like that. So there is this interesting questions now that okay, what is the mechanism? Okay, this strongly bilayer correlated phases in this bilayer material that we are talking about. Okay, so one big question is that okay, is superconductivity is originating from the correlated insulating phase, or there is a competition? So is there a parent-child kind of relation, or actually they are competing with each other? Also, means what means there has been further theoretical studies and things like that, which says that there is they are topologically, means there is non-trivial topology, effect of non-trivial topology. So what is the relation of topology there? So these kind of questions have been there, and then there has been but this is a very complex system, so you just cannot do any so-called ab initio calculations. Okay, so there has been different effective models and things like for example, there has been studies, theoretical studies for explaining them, like is it phonon driven superconductivity, or is it some extended Harvard type of so in extended Harvard there is this ideas of assisted correlated hoppings and things like that. So that has been tried, and these bands I also come to it a little more. The bands, you will see that there is a certain Born-Haber singularity that happens there. Okay, so what is the role of that? Okay, means okay, what is the role of topology? Are all magic angles topological? So these sort of questions that's going on, and theoretically many approaches have been taken and many theories have come, but from different angles. So there is no uniform understanding, or that everybody agrees with. So what we can do at this situation? So our then idea is to do a quantum design a quantum simulator, and that we will enter now. But let's see that why these kind of systems are very difficult to solve from little bit of information perspective. Okay, so as I said, okay, let's say that there are many important applications like Morey phenomena that we are talking about, or high superconductivity, or whatever is there. And why we cannot solve it in classical computers like these large systems, that we really want to know what's going on there, and then maybe that we find some applications from there. It's because it has to a lot of do with the inherent entanglement in the system. So if for example, here I am showing this one. Let's say there is a square lattice, and you have a some low Hamiltonian sum of some local Hamiltonians. Okay, and they are bounded. Okay, so they are not unbounded. In this, and you can create, let's say that you create a boundary like that, and you are trying to see what is the von Neumann entanglement entropy. Okay, that content within this area, and if it so what happens that if local gapped Hamiltonians, they has this something which is called area law. So it's the entanglement entropy increases with the area, so it's not a volume law. Okay, so what happens if you deal with 1D, then this entanglement becomes almost constant, let's say. So then we can deal with bigger systems, because as long as there are a lot of entanglement in the system, then the information is scattered throughout the Hilbert space. But when there is this area law kind of things, at least for the gap system in low dimension, then the information is actually hidden. Hilbert space is pretty big, okay, but information is actually hidden to very small area, let's say. So let's say that this is your total Hilbert space, and this green region, this is where your information is written. So if you know how to distill this information, then you can solve the system. So that's how you can solve do this. So this is the basic philosophy of this, this DMRG or all tensor network kind of formalisms that's going on nowadays. Okay, so they will work for gap system, but forget when you have gapless systems or things like that. Okay, so only special cases of quantum any-body physics can be solved efficiently. So this is the uh, hard part. Okay, so it doesn't mean that we cannot do anything. So the idea is that, so if we cannot do calculations like that we want to see the effects of correlation or things like that, then we have to do something. And here comes the ideology of quantum simulator. So by the way, if you have any question, then you can stop and ask me. It's all right. And also I'll keep a track on my time. So okay, it was pieced by Feynman first, but so when we cannot do this kind of calculations on classical computer, then this idea that was pieced like something like that, maybe then we can use a simpler and better controllable quantum system for simulating and understanding the target system. Okay, so such systems, then it will work like a quantum computer, but it's a quantum computer of special purpose. Okay, so its idea is very different from the digital quantum computers that we usually, when we talk about quantum computers, that we know about. But its idea, a quantum simulator, is that, for example, that we are trying to understand a specific phenomena. For that, we will trying to design a specific system, but it's controllable. Okay, experimentally controllable level or things like that. We'll change these parameters, we'll tune, and then we'll record the things, data, and from that we will understand the physics. So this is the idea of a quantum simulator. Okay, so let's move forward. So let's see that, okay, well, there can be defined set of platforms where you can design this kind of quantum simulators. For example, ultracold atoms, it can be ion traps, it can be superconducting devices or photonic devices. But what we are going to talk about mostly ultracold atoms today. Okay, so you can think, okay, whenever you talk about some solids or things like that, so you have some periodic potential, right? And then these periodic potentials are made by ions. So we can create the similar kind of potential by optical interference. So you can take lasers, or you can just take laser lights, and you can use counter propagating laser lights, and then that will create standing waves. And then you can trap neutral atoms there. So what we are going to do, we are going to change the role that's played by ion by some, by some light. And then the role of electron will, it will be captured by some neutral atoms. So this is how we'll try to understand the physics of a solid by a quantum simulator that we are designing via ultracold atoms. So any question? Yeah, no, up to now. Okay. So why we are interested in this? Let me again stress on this fact that here everything you have precise control over. So let's say that you can control your tunneling. Okay, you can control the interaction between the atoms. So it can be very precisely controlled. There in cold gas, there is this very efficient techniques via which this can be done. So you have a completely controllable system. It's not very different than when you are doing a calculation on your paper. So you will just tune your system, and you will you will get your data. Okay, so just a little bit of this ideas that how it's done in ultracold atom, like means why you need neutral atoms. because there can be both fermions and bosons, both are available. Obviously, we are talking about composite systems. So it can be composite fermion. You take a neutral atom depending on its isotopes. It can be composite fermions or it can be boson. So, first. Second, that they can be optically trapped. We have discussed it. So you can create lattice structures, or you can also think simple harmonic trap or things like that. There are also ways of doing that. And what happens that when you shine light on this neutral atoms, they will induce a dipolar moment on the neutral atom, and then this dipolar moment will in turn will interact with this electric field of the laser, and then with this spatially varying intensity, you can actually capture it. And also, obviously, it can be cooled to absolute very low temperature, sub-nano temperature, and then it's very close to the physics going on at zero temperature, and that's where we are mostly interested. Okay, so then we can look into these interesting physics that are going on. Okay, I'll move to the next slide. So I not spent much time here, but here there are like a couple of experiments just to motivate that. Okay, so this is just this is a very mature field actually. Ultracold simulators is very mature field going on for a couple of decades now, and very beautiful physics has been observed. That has not been, these are condensed matter phenomena, but condensed matter physicists have not been able to observe them because often the solid materials cannot go to that low temperature, or there are randomness, disorder, things like that. So but here you can create clean systems and everything can be studied. Many things has been studied. For example, it's an early 2002 paper, okay, that created a lot of buzz, was this creations of Allahabad model. Okay, so there, if you look into this picture, so this is the thing. And so actually they are looking into momentum distribution. It's in position space. Okay, so you can see that there is a change from superfluid to superfluid. So here actually this is superfluid, and somewhere these are superfluid, somewhere there is crossing, and then there is insulating phase. So this you have to do a Fourier transformation to get it, because this is in momentum space. Okay, and then more stronger cameras has been developed with time. So then you can literally see the position of the atoms now. That where the atoms are sitting, you can take pictures and see where the atoms in real time. You can see where the atoms are sitting on which particular lattice size and things like that, and you can do spin dissolved experiments also. So for that, there has been studies on Fermi-Hubbard model. So that's like one of the most interesting models that we really want to know what's going on, because you see that so many interesting phases are there, like antiferromagnetic phase, and then there is a superconducting dome also, and then there are certain phases there are a lot of debates. Okay, and even this Fermi, this superconducting dome, that's also there is a lot of debate that is it really superconducting dome or not. So if we could do an experiment like that, then it would be good. So the experiment so far could show us this antiferromagnetic phase. Okay, so this is like this one. So the temperature they could reach up to this, something like that. And actually what happens that when you are dealing with fermions, they are very difficult. There are a lot of losses. In bosons it is a bit easier, and so ideally one would like to go to this kind of temperature to see if they can to look into this superconducting dome, but this has not been achieved. Okay, and then the further studies on some correlations, spin correlations and things like that has been done. A lot of more experiments has been done. For example, localization like Anderson kind of localization, but by some quasi-periodicity. That has been studied, or many body localization that has been studied in the Manuel block flow. Okay, so many things has been studied and confirmed through ultracold simulations. Okay, so this is the background of ultracold simulations. Now let's now I hope that you remember what I was talking about. We are talking about some this twisted by bilayer graphenes and things like that. So what is our idea? Our idea is to design a cold atom simulator and then manipulate its parameter. Means we know that there will be parameters that we can manipulate very flexibly and with high precision. And then through this simulator, we want to at least, if this experiment is done, get some key microscopic understanding behind the origin of this strongly correlated phenomenology that we are talking about in twisted bilayer graph. So, so what is our aim? Our aim is to, so these are our aims. So when we will try to say, design the simulator, we have to remember the key aspects that's happening in Twistronics. Okay, so obviously the effectively capturing the essence of the twisting of a bilayer, and what are they? They are like achieving the band structures, sharing the same features that magic angle twisted bilayer graphic provides us. So that's the beginning. Okay, that's, and also if we really want to attempt even something, so we cannot really do much with this lattice sites where you have means unit cell where you have thousands of lattice sites. So there can be 10,000 lattice sites in a single unit cell. So how to deal with that? We cannot do that. So can we design something where our supercell, so these are called supercells, okay? When you are creating this artificial unit structure with different unit cells, so colloquially they are called supercells. And so we want to do the similar kind of band structure and things like that, but with a much smaller supercell. Okay, so that's there is some possibility of doing some theoretical calculation if it is possible. Okay. Also, we want to make it non-trivial, associate some non-trivial topology with that, these band structures. Okay, which is also seems like one of the hallmark of this different interesting correlated phenomena that's happening in this twisted bilayer graphene. What more? Obviously, we want to see that when there is this flat band that we create, then how superconducting is being affected and things like that. So these are the prime mottos that ideally we like to deal with. Okay, so first proposal came from CIRAX group. So CIRAX group, they had a very straightforward proposal. They said that, okay, create one optical lattice, and you can create optical lattice. You can create a square lattice. You can, if you want to create a graphene-like structure through orientations of light and interference, you can create a graphene-like structure. Okay, so you can create a lot of you can create a triangular lattice or any design you want to create. You can create using lattice and its interference. So they said, okay, let's create this kind of lattice and then just do a play with their relative orientations. But what happens? First thing will be that it will be very difficult. So this proposal of got published, but then the immediate problem that one can identify that stabilizing this sort of two optical lattices when you twist with respect to each other is very difficult. So it's not very easy to stabilize them. Secondly, samples are intrinsically mesoscopic. You have to understand this part because when let's say that so on the left yeah, so this so this is like a solid. So one lattice side to another lattice side, the distance you can think of the order of 10 to the minus 9. But typically in cold gas, the distance between atoms are something like micrometer or something like that. So and then we also have difficult means optical lattice. It's not there is scalability issues. Okay, so you cannot create arbitrarily large lattices. Okay, so then how to actually create these unit cells and how to then get the physics? Okay, if you want to get a magic angle physics which contains thousands of supercells, you cannot achieve it through this proposal, actually, to be very true. So this is, so you have to think something bits, differently. So we teach an alternative idea. The idea is following. So this idea has one key aspect that is important to understand, and this aspect is that what happens when physically what happens when you twist one layer with respect to another layer. So you will see that there is a, so when you don't twist, when you just put relative orientations that twist angle 0, so they are just orientations on top of each other. So then all the interlayer coupling. So obviously you put one layer on top of each other, then these two layers will talk, there will be interactions, right? So then this interlayer tunneling, this is uniform. But when you rotate, what starts happening that you are spatially modulating the tunneling. This spatial modulation is the key aspect of beautiful physics that you are seeing. I don't know if this part is clear, but maybe that okay. Let me make it a little bit, visualize it a little bit differently. Let's think that you have a solid material, okay, and the twisting that you are doing is not very different than thinking that you take two materials on top of each other, don't do any twisting or anything, but then you apply different pressures at different points. What will happen then? Because you apply different pressure at different points on that material, your interlayer tunneling will get modified. So effectively, then also you are creating larger unit cells and the different materials altogether. So this is the key idea. When you recognize that, then you know that, okay, if you can play with the spatial modulation of interlayer tunneling, maybe you can create something like that. So this is the concept. And then this concept is based on these two key ideas. One is synthetic gauge field in synthetic dimension. And second is spatially dependent Raman coupling. We'll introduce these concepts, but how am I doing on time? Can you tell me?
Sir, you have around 15 to 20 minutes.
Okay, 20 minutes. Okay, so I thought that, maybe I have spent a lot of time in the introductory parts, but I think that the basic idea could be needed to be introduced. So let me say that what is the idea of a synthetic dimension? So synthetic dimension is like that, let's think there is an atom, okay, and it can be in a lattice site, but it has many internal, internal states. Okay, so there can be hyperfine states, or you can play with the this. You can then what you can do, you can shine a light, and then you can so you can Raman couple them actually the different layers, not different layers but different internal energy levels. When you do that, you can this coherent Raman coupling that we are interpreting as a tunneling between one internal state to another internal state. So that's giving you an artificial dimension. So this is an interpretation of the same thing of a so I can couple these different internal states by light. Okay, so I can drive my atoms from one state to another state through this light, but then I am interpreting it as a dimension. So this is one thing. So when you do it, you are doing it like so there will be it will bring a phase actually. So this does another thing inherently. So neutral atoms, if you sign means neutral atoms are not like electrons really. So it will, you know what the effect of an electron when you put it in a magnetic field. See, you don't get that, okay, in neutral atoms. So, but effectively, what happens that when you go from one lattice side to another lattice side, so it will pick up phase, and then you can see that you can get a net flux in your system like this. Uh, I'm not getting this laser pointer. Okay. Yeah. So yeah. And then that you can also tune this gamma, okay, the phase. So this effectively, like you can think that you are getting, if this is your Hamiltonian, I am writing. So you can do these sort of things with alkali atoms, which means many of the alkali atoms has a large nuclear spin manifold, and you can couple them by lights. For example, you can strontium or terbium, you can do experiments with. So for they have I think strontium has I equal to 9/2 or something like that. So there's so many levels you get. And then what you can do is that, so there is, now look into this Hamiltonian bit carefully. So there is one physical tunneling. Okay, so this is like going from one in the physical dimension, going from one lattice side to another lattice side. And this is what is we are doing it by light. Okay, so we are coupling the different internal states by light. There is a phase associated, and this, and then so this M is actually the index for different internal states. And then this effectively is like giving a momentum kick. So that's what you get, right? When you write your effective Hamiltonian, electron Hamiltonian or Lagrangian in a magnetic field, what do? You bring in the magnetic vector potential, right? And you change your momentum by something. So there is a momentum shift. And exactly this is what happens here. So it's like you are giving a momentum kick here. And your momentum gets modified by by this gamma phi. I will speed up a little bit, I guess. Otherwise, yeah, I'll speed up a little bit. So okay, so this is the little bit about experimentally how we try to propose. So we'll need three different kind of lasers. One kind of lasers is for creating the optical lattice, square lattice structure. We'll play with only square lattice structure. Originally, the physics in solid state is happening in honeycomb, the graphene. But we say that it's not required. Okay, you can get the similar physics in square lattice. So we will sign lasers to create a square lattice optic, that structure. Then we will do this Raman coupling. So these are like you have these Raman lasers. So you will need a pair of Raman lasers, and you can play with this relative orientation. Okay, so like this theta, you can play. In principle, it's easier to make them counter propagating in the experiment. But you can change the relative angle. It's not a big deal for the experimentalists. So and by this you can control the gamma that I was showing. Okay, so the effectively what I related with the flux or momentum key. Okay, and then what more do you need? You need a special. We said that we need a spatial modulation in interlayer tunneling. So our interlayer, what is our interlayer? Our interlayer is this tunneling between different internal states. Right. So we want a spatial modulation in that. So this part is a bit tricky. It means I will not explain a lot, but there is something like there is a modulation laser that can be introduced. So this additional modulation laser that you will need here, and then this modulation laser actually creates a large light shift in this 3p1 state here. So this 1s0 to 3p1, there is this detuned, coupling between these two states. That's like Raman coupling. Okay, and then you will see there are these green lines and so something like red, not red, this orange. So these greens, you can think they are like two layers. So you will need at least four internal states. Two will play the role of two, internal state will play the role of two uh, planes. Okay. And rest of the two internal atoms, internal states will play the role of two spins, like spin up and spin down in a electron. So this is the idea. So this modulation layer will create a modulation in my tunneling pattern that we want. Okay, so this can be done. So this is not very different from, you think, like you see so many holography. Like so what is holography? You are taking light and doing some intensity, amplitude changing there. So you are playing with the intensity and you are creating different structures. It could be, India's flag or something like that. So similar kind of, concept you can think like this kind of intensity modulation, it can be done. Amplitude modulation, it can be done, and it can be imprinted on that laser that we want experimentally, and then we can create the spatial modulation, any modulation we want, even quasi-paving modulation we want, it can be created. Okay. So this is the beautiful part, and the modulation that we consider is like this. Okay, so this is omega 0. This is like the amplitude, and so this omega x. So this depends on this x and y. So this is like the amplitude, and this has certain periodicity, Lx Ly. Okay, depending on that, depending on the your value of Lx and Ly, you will create different unit cells. Okay. And how does it depend? This omega 0 depends actually on this inversely proportional. So alpha is inversely proportional to delta 0. What is delta 0? This is d2. So if this is like omega 1 and omega 2, so this your omega 0 something like omega 1, omega 2 by delta 0 by the d2. Okay. So now we can play. So now we have this. So now we can play with, we can change our Lx and Ly and try to study different things because we are creating this supercells. So we'll see that whenever our Lx and whenever our Lx and Ly is for new, when new is 1, 2, 3, we are creating band structures like this. Okay. So we take a square lattice, and then obviously we have two layers from these two synthetic, tunneling, and then we introduce this modulation. We put Lx and Ly equal to 4 new, and it can be any integer values, and you will see that this kind of band structures are emerging. So there is one flat band, okay, degenerate flat band, and then there is Dirac, and so this is like the high symmetry, a cut in particular in the high symmetry points, along the high symmetry points. Okay, so this is just a projection along the high symmetry points for better viewing. You can see, and this is the density of states basically. We can do a perturbative calculation. I'll not go into details, but you can see this width of this structure that emerges. So actually there is a particle hole symmetry. Because of that, there is negative spectrum and equally positive spectrum. So you can play with both of them, but we have just showing the negative spectrum where it's emerging. Okay, so actually it's not the entire band structure. So there are others, but we have only isolated the part that we are interested in. And you can show that it's proportional to cos gamma, and this width of this quasi-flat band that we can also calculate perturbatively, and you can show that's proportional to t square by t square cos square gamma by omega 0 alpha. So what happens that if I can control t, if I can control omega, if I can control alpha 0, if I can control omega 0, we can control everything. We can control the band width of these flat bands. We can control, we can do so beautiful things because the bandwidths are now controllable. We can make it flatter and flatter. We can make it wider, or where they are now. So because why we can do that? Because in ultracold atoms, everything here I am talking about is control level. So we can precisely change it. we can precisely control it. So this T can be controlled, this alpha can be controlled, this omega 0 can be controlled, this gamma can be controlled. So many options you have. So this is the playground that we offer. Okay. Now we are not talking with about topology. So for doing topology, you have to do something. I will very quickly go through this part. Okay. We have to do something bit more. Okay. So what we have to do is first you have to. So you see that there is no gap actually here. There is actually, if you zoom into it, you will see there is only a local gap here, but it's not a global gap. Okay. So if we want to see role of topology, things like that, you would like to see some gap opening or something like that. So what you can do is that first you can break this sublattice symmetry. So you can introduce some on-site potential, or in colloquial language, is also called chemical potential, but on-site potential is the more correct term. So these pink sites, they are, I will put some on-site potentials, and I will also introduce next nearest tunneling, but it will have a complex phase associated with it, direction dependent. So I will not go, but we have also discussed that how to experimentally implement this kind of thing. We have proposed that, but I will not go into that. Okay, so what happens? This magnetic flux that I initially talked about, that opens only a local gap. But this so if you can do two things. One, you can do dimer. You can take a tunneling dimerization like T1, T2, T1, T2. That will also work. Okay. So this creates a hard gap. Or you can take a phase modulated next nearest hopping that I was talking about, but there is a phase modulation. So that also opens a hard gap. So, okay, so we are creating from a band structure like this to this. Okay. But this mechanism will destroy the Dirac points. Okay. So immediately, as soon as you introduce this on-site potential, what it does is that it introduces a mass term in your system. And then it no longer this massless Dirac like this. So then you are creating these gaps. Now what you can do is okay. Here is a very basic. I am not going to talk about it, but topology is followed. You can what indicator we will use. It is Chern numbers. The Chern number is directly associated with integer Hall current that we know about, and so this is the relation. If I so this is the relation. Okay. So let's say that you feel your electrons or whatever the atoms up to your Fermi level, then and then there are different bands. You have to calculate the Chern number of the total Chern number, and then this is related to with the Hall. So if there is a non-trivial topology, that means you will have non-zero Chern number. Okay, and if it is a zero Chern number, then you will have zero Hall current. And how to calculate this? What is this Chern number? They are they are certain kind of topological invariant. Okay, they are directly related to Berry curvature, which is followed from Berry Berry connection, and they have to be. You have to go to momentum space and to look into block wave functions, and through that. But you have to remember that in our systems, our band structures can be degenerate. So we have to calculate a non-abelian variation of these curvatures. So there are some ways of doing that, and once you do that, you can see that for this there is a critical on-site potential below which these two top bands are non-trivial, and the middle flat band where we are mostly interested, this is actually trivial band. But above the mu greater than mu c, above the critical value, this top band becomes trivial. Okay, this band becomes trivial, and this band become non-trivial. So we have created a flat band which has non-trivial topology. Okay, so this is the thing. So trivial means all the Chern numbers are zero. Standard non-trivial is like when we are saying this is -1, +1, and 0. And that's non-standard non-trivial is something like when you have -1, 1. So these two numbers get switched when you cross. And then it's obviously you can see that what's happening when you are below. So there are these red dead points. These are like the edge modes. And this is what it's showing here. So there is the bulk boundary correspondence. You can see the edge modes. They are responsible for the Hall current, right? And but above this, your structure immediately get changed. You don't get any edge mode here because this is now trivial. Okay, but there is a edge mode here. Okay, so this is what, and you can see explicit structure of these edge modes, that how do they look like, probabilistic description, and you will see that they are at the edge of this 2D structures that we are creating. Okay, so it's like this, but for this one, it has a very funny, some non-asymmetry is coming. So it's not symmetric like this one. The edge modes that's coming. Okay, then I will not spend any time on it, but we will say that we have done some now. So far, we are talking about this single particle level, but then we can do more studies with interactions. Okay, so we can take typical. So you have like 4 kind of interlayer interactions. You can do all different kind of interactions. Now, in cold atom experiment, the interaction can be changed by various tricks. Phase wave resonance is most probably is not a good trick for this. Because we are dealing with fermions in lattice, but still you can play with this, tunneling to interaction by quite a bit by varying the transverse confinement. Phase wave resonance, there will be a lot of losses and things like that. So, so what happens that we have originally so we are dealing with this 4 levels. So there is this SU for symmetry. What SU for symmetry mean that if you don't break the symmetry by some other means, then there is this collisional. There is no collisional redistribution. What I mean, but by interaction there won't to be any spin flip or something like that. Okay. So now, or you can explicitly break the symmetry, by selective tuning of interaction channels. Let's say that don't. But then there are now it's very complex, but you can do something like multiband Hartree-Fock, Bugler-Fock type approaches. Okay, which will you have to compromise on your correlations here, but it will give you at least some hints on superconductivity, things like that. So we have started fractionally filled cases, in solid bands like 1, 4, and 3, 4. And the flattening of the bands in the vicinity of Fermi energy leads to opening of a superconducting gap. So that's the first observation. Second observation is band flattening causes a critical temperature scale to significantly, so the critical temperature significantly get increased. Okay. And then there are other things like, talk about it. So this is my concluding slide, and what I will finish it with this summary, which is not the thing that I have talked so far, but overall things. So some means I'll just remind of the advantage of Ultracold simulator that we are proposing. One is that we can manipulate this intra and interlayer tunneling strength with wide ranges. Okay. So this is this can be manipulated, this can be controlled. Second is that manipulation of atom-atom interaction. So this kinetic to interaction energy ratio that you are believing that will give you interesting physics, it can be also tuned to large ranges. Okay. Secondly, these are very clean systems. You can think they are very much isolated from the external environment. Okay. There are problems like when you deal with fermions or things like that. There are problems with the losses, but still it's very. There are a lot of less fluctuations, and we also have designed something that has a very less number of unit cells. I didn't talk about this, but when we are getting this, when Lx equal to 4 and Ly equal to 4, when I talked about that, we have a supercell. There are like 8 lattice sites on it. So this is we are not now talking about something which are 10,000 lattice sites in a single supercell. We are talking about a supercell which has all the possibility of giving us a similar kind of physics, but only with 8 lattice sites. Okay. So in conclusion, I will say that mode phenomena, this is just we are scratching the surface of all the possibilities that it can over. So it's really a school of physics that involves quantum optics, material science, condensed matter, quantum information, many different aspects, and you have to come from different directions to understand this. There is no just unique expertise that you can apply and understand, but you have to come from different directions to get a consolidated understanding of the system. Hopefully, with time it will be done. And these are some of the references from our work, and you may look if you want. So this is a QIC group at HRI. We have a very large group. There are 3 faculties and another visiting faculty, many PhD students, many visiting students, quite a few postdocs as well. So if any of you are interested to come and visit HRI, we will be very happy to host you. Let me know and write to me. Thank you.
Thank you, Debraj, for such a nice talk. We should have questions now. Please unmute yourselves and ask the questions.
I have a question, a small question.
Yes.
So what other phenomena we can simulate using these ultra-cold atomic systems trapped in optical lattices, like apart from
The most strange thing answer that I will say that people are trying to simulate high energy physics using ultracold. So this sounds crazy, but it happens. But gas theory, then that is gas theory. But you all sort of you see you tell me that one phenomena that you have, like magnetism done, topology done, superconductivity done, localization done, many body localization done, for any particular quantum phase like Bose-Hubbard done, Fermi-Hubbard done. Okay, obviously what's challenges with ultracold atoms that when you deal with fermions, and most of the times this is very interesting physics are coming from fermions, okay, not from bosonic. People are still struggling to go to that temperature where it's really needs to be. For example, when I was talking about the Fermi-Hubbard model, there is a recent, like couple of years before, there is a recent discussion, like a lot of debates, like this: is it a really superconducting dome? So they have done, machine learning. They have done 2D tensor network, all sort of things that people can think of. It's a very large collaboration, large number of people are there, and their final conclusion is that it could be a stripe phase, not a superconducting phase. So this is there are debates. Always these theoretical debates are going on. Okay, so for if this temperature could be, now I think they are close to picokelvin. Sion may, confirm this, that which temperature exactly. Samnanu for fermions, I think they still could not go to picokelvin. And so
it's T by TF, right? So the basically
yeah.
you can't get it to the temperature which would be below the critical temperature for getting the superconductivity. I think the claim right now is the best one gets is actually with these SUN atoms, which are ytterbium and strontium. Yes. So there, if you take with SUN and then you start sort of removing one of the energy level, one of the atomic levels one by one, then you can reduce the temperature, but there's also massive atom. So there's that problem.
So this is the thing, means a lot of has been done, but we still there are a lot of rooms also. But if you have any particular phenomena that you are thinking about currently, then means if I know if experiment has been done, then I can say, do you have any particular phenomena in your mind? That you
No,
want to see that? Okay. So yeah, means a lot of things are like block oscillation. This simple block oscillation that could not be observed in solids. This first confirmation of block oscillations. Okay, this is a very primitive, solid state understanding the terms, and that has been was first confirmed through ultracold. So yeah, means it has a lot of things has been done, and but there is still a lot as we are going. Like for example, unconventional superconductivity, something that atom experimentalists would strive to look forward to and understand. I'm sure that this has not been done yet. Okay, so that again that struggle will be reducing the temperatures and looking into this. Thing.
Okay. So there will be some limitations also, right?
Yeah, limitations are there. One is scalability, but this we deal with creating smaller supercells in our proposal. Okay. And second is temperature. Atom loss is basically okay. So for the there is basic source of this atom loss will be like some beyond 2 body collisions or 3 body collisions or things like that. So yeah, but I believe that the way the field is being moving and maturing, and this can be most probably will be addressed in near future.
Thank you.
Other questions? We have time for another question because we're running on a tight schedule, but we can have another question.
Yes.
Okay, if not, then we will thank Debraj for such a nice talk, and we'll move on to the next talk then.
Yes, Sion, thank you for hosting, and this is a wonderful thing that ISAR is doing, and I am very happy to give a talk. So thank you. Thanks for all listening. Shall I disconnect now? Can I disconnect?
Yeah, you